sorry, if you guys choose to move on to flagship. So the first thing we're going to do is we're going to talk about, we touched on, why it's important to learn algorithms and, some of the companies that use them. But essentially, learning algorithms and the reason why algorithms are so prevalent and heavy, the topic is heavy in interviews, is because learning algorithms and learning which algorithm to use enhances your problem solving skills. Okay. It forces your mind to get into the habit of breaking complex problems into smaller, more manageable components. That is one of the most crucial skills that you will have in software engineering. It's knowing to break it down. And the better you are with algorithms, in my opinion, the faster you'll move up in the chain, because then you can identify problems, how to break them down, who can work on certain parts of those problems, and then pull them all together. So that's my 2 cents on that. I want to talk a little about, where's my notes on? Okay. So, we've gone through like how does Google use an algorithm, right? Facebook, same thing, Amazon, Uber, Netflix, NASA, obviously, of course, Twitter. And then there's a Scikit, which is the Scikit-learn, which is open source algorithms, which are mainly used by the banking industry, whether it's fraud detection or just simply when they're looking at stocks and bonds and financial gain, they use Scikit-learn. So these are things that are important. Now, one of the things that I talk to you guys about a lot is how do you become a better software engineer other than sitting in a class or doing leak code? It's being part of a community, right? So either you're doing hackathons or you're joining like the meetups that happen in all cities, either virtually or in person. The other thing that is important is to like read, right? So you're constantly reading either Medium or Stack Overflow or any of the blogs that are out there. I specifically also read the blogs that are posted by individual companies like Google and Amazon, Netflix, NASA has a blog, and they talk a lot about their algorithms and what algorithms they're using. So it is my suggestion that if you particularly like a company and it's something that somewhere that you aspire to work, find their blog. I'm going to post all the companies that I mentioned earlier, all of their blogs in the resource channel. And if you're not interested in any of those and you're interested in startups, there are blogs on startups. If you're particularly interested on front end or back end and you can't find one that you like, just message me and I'll help you find one. And I think it's important that you go and you start immersing yourself in the language, in the ideas that are being bounced around by a lot of these companies. It's really interesting. And it's nice to know like what they're doing and like upcoming releases to their software. And it kind of gives you street cred when it comes to like conversations with other, if you're in an interview, you get to drop, oh, I just read on the Google blog, blah, blah, blah. And, kind of makes you look smarter than you already are. Or if you're at a meetup, right? People like to talk. So definitely take the time, choose one, choose two, and just read. James, you're reading YouTube's? You can come off mute. Go ahead.
No, my girl works at Goodwill, so I ended up picking up a few books on Java and a C# one, and then on Amazon about Python. And then when it comes to, like you said, the new updates and stuff, literally on my YouTube short, there'll be guys be like, well, here's a cool thing that they added to the new update of Python. You can do
Right.
this instead of having to do this.
Right.
So
So it's definitely immersing yourself in the industry is critical to your knowledge base and how your knowledge is being applied in real time. So, okay, so now we're going to jump into breadth first search and depth first search. Now that I'm off my soapbox. All right, so let's talk. Oh, and I wanted to mention, so like if you have Facebook, right? And what is the point in depth first search and breadth first search, which are basically traversing on trees. So, and you can use it to traverse, you can use both traversing algorithms on queues and other data structures too. But, I wanted to talk a little about like, so you have a friendship chain on Facebook, right? And you think about what is the purpose of a short path, right? And like, so you identify the shortest path between an individual helps you reveal their friendship chains as Facebook calls it, connecting people. So Facebook will, or Meta will often analyze the shortest path to understand how individuals are connected to their mutual friends. So if your mutual friend is like, if you don't have the same last name, right? So it assumes that if you have the same last name, that you're related in some way. But how you're connected. Are you connected through schools? Are you connected through a social like group? Are you connected because you're neighbors? So it goes and it tries to figure out how you and your friend are connected socially, right? And then it goes and it tries to find other connections based on that identification, right? And that's how it builds your network. LinkedIn does the same thing. And finding the shortest path is how the algorithms work. Okay. And it's how they very, very quickly identify information about you, right? What you're clicking on. Like it's almost instantaneous. You click on an ad and you immediately start seeing ads about those particular things. I'm sure, Paul, you're looking up, all this stuff about your computer doesn't work and you're having all these lagging issues and you're going on different sites. It's going to start showing you ads on that information, right? The 6 degrees of separation, 7 degrees of separation is where the shortest path comes in, right? Two people are connected in the world. How are they connected? And then how can they take advantage of that connection? Okay. It's not notorious, but it is just what it is. It's part of being part of a social network. James, you had your hand up.
I was gonna go on the depth first search because you were talking about graphs and stuff. So like how a banking thing would be like you spent this much money and we divided it into
Mm-hmm.
these categories.
Yeah, absolutely. So it's like one of those it's such an interesting concept of data mining and data like pulling and creating these assumptions about their users, right? Which are very, very monetarily successful, right? And that's, anywhere you go, you're going to be using breadth first search and depth first search if you're doing backend, anything with data, right? Okay, so we're just going to jump right in. I'm going to share my screen. And before I do, does anyone have any questions? No questions? Yes, code is open. Why can I not see the share button? There it is. Everyone can see? Awesome. Okay. So I'm going to go back to the concept of, okay, what is a tree, right? And so you look at a tree, and the tree looks like this, right? So someone tell me what this is. What is A in the tree?
The root.
Okay. And what are these? James, don't answer because you don't have to answer them all. Someone else answer that doesn't really speak in class. I want to hear from everybody.
Are those twigs?
Sure, they're twigs, but in all seriousness.
Branches.
What is the technical term of those?
Edges?
Edges, absolutely, they're edges. Okay, no guessing in coding. Okay, what are these? Come on, there's 20 people in the room.
Child nodes?
They are childs, absolutely. Okay, they're children of the parent. The parent is the root, and these are children, right? And then you have a left and you have a right. So it's really important for us to understand the levels and how the relationship works, right? Okay, so in breadth first search, right, it starts from the tree root or any arbitrary node, right? So whatever we choose, right? And it explores the neighbor's nodes at the present depth before moving down, okay? So it'll explore A, level 1, and then it'll go to B and C, and then it'll do D and E, okay? That is the difference between breadth first search and depth first search. And it's a critical difference. So when we get to depth first search, I'll explain how that works. So, when you do breadth first search, you're going to use a queue, right? So does someone want to refresh everybody's memory about what a queue is? What's the order a queue works in? How about that? Let's start with
First in, first out.
it is not first in, first out.
LIFO.
Yes, so river. It's
First
LIFO, right? So a queue is just like a movie queue, right? Is a queue a movie queue? Last in, first out. It's a LIFO.
Oh, LIFO.
It's a LIFO. So last in, first out. So it's opposite than a movie theater queue, right? In a movie theater queue, you're going first in, gets in first, right? So it's first in, first out. So it's LIFO, as Andrew and Niaz just said. Okay. So how do we set up a queue, right? So what we want to do first is we want to create our queue, right? So we have to import the library that allows us to use a queue, right? So does anyone remember how to do that? Which library am I going to use?
You're gonna import deck from collections, import deck.
Yes. So that's how we import the library that has the data structure of a deck, right? So it's very important. A deck is not inherently part of the Python out of the box library. You have to import collections to use a deck. Okay. So again, I'm just going to create, I'm going to create a function, right? And we're going to call it BFS. And I'm going to say it's a tree, and my parameters are tree, and where am I starting, right? So then I'm going to create the queue. So I'm going to say queue equals the deck. And we're going to start with, so to create the root, right, we're going to use start. That's going to be the top of the deck, right? Because we want to begin from here. Okay. So that's going to create our queue. And so now what is it that we want to do? So we want to visit each one of these, right? And we're going to add them to the queue and then visit with that. So basically when people use the term visit when they're speaking about trees and traversing, it means that you are going to put this either, if it's breadth first search, in a queue or depth first search in a stack. When you visit a node, that means that you're doing something with that node, right? You're actually performing some kind of task, a Boolean, checking its value, checking who its neighbor is, whatever. But visiting means that you're doing something with that node. James.
So in a way, you could use this to find a target node.
Yes.
Yeah. Okay.
So it's used often in gaming, right? The shortest path is something that is often used in gaming. So, okay, so then we have to say while there is a queue, so while the queue still has something in it, right? We're going to essentially, I'm going to put the code up and then I'm going to go through what we're doing, okay? We're going to go through it step by step. Paul.
Hey, I just looked up queues. Unless I'm missing something, it's saying that it's first in, first out. Cause I just think of queues as being in line for something. Yeah, that was it. I just don't know. Maybe, if it isn't, then could you maybe, I don't know. That's it.
I'll bring it up and just I'll go look it up again, but now I'm like, is a queue. Now you just no. I'll look it up and we'll get to it. Not a big deal. Okay, so this is the breadth first search. So you're going to ensure that your queue is populated. Okay. Then we're going to the node equals, you're going to pop left off your queue. So from the left hand side, whatever's in the beginning of your queue, you're going to pop that one off. Okay. Then we're going to do something with that node. In this case, we're printing that node. Okay. And then we're going to enqueue the child node. So what's the difference between enqueue and dequeue? Anybody remember?
It's NQ is add and DQ is remove, right?
Yes. So we're going to add. So once we do something with A, right? We've printed it now. Then we want to add the children to the queue. So it's going to be left to right, right? And it's going to add B and C. Make sense? And then it's going to do something with B and C. So the first iteration that happens is, this is what happens, step by step. Okay. So the first iteration is, let me do this so it's a comment. Okay. So your first iteration is you're going to start with A, right? You're going to enqueue A, right? So, and then you're going to visit A. So visited means I'm going to, whatever I want to do with it, right? The next thing that happens is what happens next? It printed A, it did what it was supposed to, right? The next step is it dequeues A off your deck. It prints A, it enqueues B and C, and it marks A as visited. Okay. The next step.
So is it kind of like it's just for visualization? It went to A, checked its ticket, put the ticket in the line, and then went to B and C to check their tickets. Okay.
So that it dequeues B, right? It prints B. It does whatever it's supposed to do. It enqueues. This is your enqueue, right? So in your queue, you have C, D, and E. And now it's marked that A and B are visited. Okay. So then we just go down the line, right? So the nodes are going from being in queue to being visited. The next step is it dequeues C, it prints C, and then it enqueues D, E, and F. Right. So pulled in E and F. It pulled in F at this point, and it marked A, B, and C as visited. Right. And then we go, so I'm just going to copy my notes here. So I don't.
Now, does it do it until the results are null? So like A is the root, and then say B doesn't have any children, and so it nulls, and then it would go to C to make sure that there was no node underneath.
Right, so it's making sure it's going left to right. Right, so you have
Okay.
A, that is doing B and C. We're in breadth first search, right? In
Right.
breadth first search, it's doing it by level.
Oh, okay.
And it's going left to right.
Okay.
Okay. Okay. So then it DQs D, it prints D, and in your InQ you have E and F because that's all that's left, right? Oh, I don't have an F. I'm sorry. Well, if there was an F, and then it marks A, B, and C, A, B, C, and D as visited. Okay. So any questions about what it's actually doing? Right. Okay. So let's do an example of visiting all of, let's do a full class. Okay. And again, we're practicing classes because it's something that it's not as simple as doing functions, and you want to make sure that you get more and more comfortable with using a class. So we're going to create a class. I'm going to call it tree node. Okay. And I'm going to do a init. And I'm going to do self and data. Why it's being mean to me right now, I don't know, but is there something else I'm not?
Missing a space
All right.
after def.
Yep. Thank you. Okay. Good eyes there, Mr. Patrick. Okay, so I'm going to do self.data equals data, self.children equals empty data. Okay. Now what? So then I'm going to do, let's create our tree. So I'm doing A equals tree node A, and then B, C, D, E, and F. Okay. Now I want to create the children, right? So I'm going to say A's children are B and C. So A dot children is B and C, right? B's children equal D and E. My cap's on. And C's children, oh my Lord, equals F. Okay. So then what? So now I want to call, what do I want to call? How do I call it? Anybody?
Print A, print A dot data.
Yeah, we can do print A dot data. Okay.
A dot data, what? A dot data, B dot data, C dot.
Okay, let's see what
C
that's
dot
like.
data.
Okay.
Or I'm
that what
guessing
you want?
if you're going to do them all at one, if we're going to do them all in one,
Okay.
A dot data, comma.
Okay, let me just do that. Let's just see if it prints it, right? This is week 14. Right? Okay, so that's what it's right. So you would have to then do b dot data, or you could create a loop, right? You can create a function to create a loop to print through the entire thing. Okay, so then you have, so let's go through, let me do this. it's really just as simple as these 5-6 lines of code, right? All you're doing is printing one after the other, right? So if I run this function, right, BFS, right? So if I do BFS A, what's it going to do? It should run the whole thing. Oh, I didn't do a start. So what do you want to start with? Do we want to start with A?
Well, yeah, wouldn't A be the root?
Okay. I hate when my code doesn't work in front of you guys. It's telling me that it can't. I commented this out, so let's try it again. Okay, so there's your, this is Patrick's, right? I'm sorry, Wesley's, and then it gave me A, B, C, D. So it's printing, it goes through, and it's doing all of this, right? It creates the tree, then it creates the deck, and then it's doing everything here, right? Right, so then it prints, where's Wesley's printing? Let me take this out. So if you wanted to, instead of printing it, if you wanted to like say, is your node, so instead of here, right, we're just printing. If you could put a Boolean in here saying, does A equal a value, right? That's what this is where you would put it. You would simply just put it right here and say, if the node equals something, stop. And then it'll stop, right? So it's traversing level 1, level 2, level 3, and it's going in that order. So a lot of times they'll use this code when they're searching for your your 6 degrees or 7 degrees of separation. They'll say, okay, how close are you to the parent node, the root node, right? And how far is that separation? And then they rate that separation, okay, as to how much in their minds your data is investment and your connections are investment. So how much weight should we put on that connection, right? How many times did you search? You know, Paul, in your case, how many times did you search for your hard drive, right? And it keeps track of like Amazon keeps track of all of those things, your Google searches. So so it'll go through and say, okay, how many degrees are all of these searches from each other? And what is their relationship? And then weight it. Okay. So this is not a complicated, so the words are very complicated. Breadth first search and depth first search. Very complicated words. It makes it very scary. But all you're doing is creating a queue with your tree. Okay. And you're putting one node in, you're testing it, and then you're in queuing the children once you've tested the root node, or you're finished with the level. So it's really not as complicated as one would think, right? It's just which direction are you doing it in, right? So that's the difference between breadth first and depth first. James.
So would this help kind of like the way I see it, you could pretty much use this to find like to go through data to find like corrupted data?
Yes, absolutely. Or unrelated data, right? It's a great way to separate data, right? To say, okay, your corrupted data doesn't match to anything, so I'm going to get rid of it. When you're talking about file structures or viruses, they use breadth first search, depth first search. Okay. Is this related to the code I'm on, or is it related in any way to the data that I already have? And if not, get rid of it. Okay. So then we can look at your depth first search, right? So what's depth first search then? You guys watched the video, right? Okay, so let's look at depth first. Let me just make a new file. Okay. So same thing, right? You have your tree. Let me put my tree back up. Oops. Okay, so there's my tree. So in a depth first search, right? Again, this is a graph traversal. It explores as far as possible along each branch before backtracking. Okay, so let's look at where did I see if this will work. What's the order? If you had to guess.
A, B, D, E, C,
A, B, D.
E, C.
Okay, so what it's going to do, you're close. It should do A, right? Then it should, in depth first search, is going to go right-hand side first. Okay, because you're stacking. Okay, so think about the way a stack works, right? So your stack is going to look like this, right? So it's going to stack A, right? And then it'll visit A, and then it'll add, then it'll become B and C, right?
So it'd be A, C, B, E, D.
Yes. 100% correct. So it's going to pop, because we're using stacks versus a queue, right? And the deck, it's going to pop off C first, right? So it's going to do A. And so you think about in DFS, it's right to left because of the way the stack works. Okay, so it's going to do A, C, go to B, right? And then as Donald said, then it goes to E and D. Okay, so let me put this up. Let's see. Oh. All right. So again, I'm initiating the tree, and then I'm going to print the tree. Donald, do you remember yesterday you wanted to know how to print a tree like this? I hope I did it right. So let's look at what's happening here, right? If there is a node, I'm going to print it with the space and then the level and then node.data. So it's going to give me the value of the data, right? And then for child in node children, I want to print the children, right, on the same level. And then I'm using an accumulator to change the level back. Here's my accumulator. Okay, so Donald, I'm going to put this, so whoever wants to print these little pretty trees, you can print these little trees. And I hope it comes out right. Now I'm looking at it.
I think it just helps me visualize it better, like when I
No,
see it, you know? It's
and I
like,
totally agree. Like I like to see it in like the little like this too, but
Mhm.
you're not that lucky sometimes because you got to remember the data that you're working on is not going to be just 5 little elements, right?
Yeah.
So you have to look at children, right? You have to look at what's the children and the dot children, right? Oh, I'm scared to run this now. Oh. So, when you do it this way, the reason it's these are your levels, right? So this is your third level, your D and E, and then your B and C are on the same level, and your A is your root. So typically when you are printing a tree, you're going to see it like this, in this format, versus this pretty little tree, right? So you have to kind of quirk your head and say, okay, what's the first level? What's my root? Who are the parents? And then who are the children, right? Or child of child. Let's use the right term. Do you see it, Donald?
Yes. So in the terminal, so A
Mhm.
like B would be like the left, and then
Mhm.
C would be the right,
Yes.
and then D would be the left right, and then C would be the right left. I'm not sure like how that works. Can you go over? Do you get what
So
I'm
this
saying?
is left, this is left, this is left, right? And then,
Okay.
right, then your D and E are left and right,
Okay.
okay?
So that would be left. Right, right.
And
Okay. I get it.
because D and E are below B, right? That means that they're children of B. If they were children of C, they would be below C at the same level as D and E. So here. G. Like that. So that's how you know they are children of this C. And because they're together, left and right. The only reason B and C are not together is because they have children. Okay. All right. So let's go through first. Let's talk about stacking. Okay. So DFS uses a stack to keep track of the nodes that it is exploring. Stack is last in, first out, and I think Paul, you are correct. And we what's it called? Set it backwards. The algorithmic steps of a DFS is it starts at the root, like we just talked about. And then while the stack is not empty, right, it's going to pop a node from the stack, right? So, and then it processes that value, and then it pushes the unvisited children to the stack. So, right, it puts A, right? Then it does C, it visits that and it does something with it, and then it pushes B to the stack and it processes it. Okay. The order in which they're processed depends on the use of the stack. If you don't use a stack, your DFS is not going to work correctly. Okay. You can also force the stack to run backwards if you want it to do left to right. Okay. I don't see it often. I don't think it's smart because then you're like complicating the situation, but it's possible that the way you get your data is it's more fruitful for you to read your stack left to right instead of right to left. Okay. So, how do I add to a stack? Does anyone remember what you say? What's the syntax?
Up. No, I'm lying. Push.
Push. Yes. So pushing adds an element to the top of the stack, and popping removes, right? Removes an element. Okay, think of a stack as your Pringles can, right? To put one in, you have to, put it from the top, right? And when you need a plate, you take it from the top. So push and pop. Okay, so we have our tree here, right? And let's talk about in the same way, how does a DFS work, right? Differently than a BFS. So we're going to iterate. you iterate, and I keep losing my first letter. So we're going to start with A. We're going to push A to the stack, and we're going to mark it as visited, right? That's what's in our that's what we've processed, or we're touching essentially, right? So okay. So then what happens? It pops A from the stack, it prints A, right? And then it adds B and C to the stack. And still the only thing in visited is A. So then what? Which one comes next?
Then doesn't it, boy, before I could even say anything, I was like, then it does the same thing to C, because you said it started on C, so go C, B, and then once it marks those as visited, then it'll go down, and then it'll go do E, D.
Yes, exactly. So it's going to pop it, print it, right? Your stack is still the same in B because there's no more children, right? And you have A and C left in visited. And it just keeps going.
And that's what I meant by null, because C doesn't have children, so it would just go down to B.
Yes. Yes. Exactly. So there it is. So here, this is your, and it keeps scrolling. This is your depth first search right here. So it's 1, 2, 3, 4, 5 lines of code. It's an if statement, meaning is there a node there? Right? I'm going to print it. And then I'm going to concatenate the actual value of your node. Okay. And then it's going to do the same thing for the one next to it. It's not that complicated when you think about the code. And this is one of those that you can memorize pretty easily. It's not something that it's like the one we did yesterday, which is, freaking 12 lines of code or 15 lines of code. You can easily remember how to do a DFS and a BFS if you just practice it. So start the root and you push it to the stack. And while it's not empty, it's going to continue down until it gets to the end. Okay, so there's no questions about what we're doing? Okay, so it's going to be up to you guys if you want to do, I think I'll leave it up to you guys if you guys want to go to breakout rooms, or if you want to, I will do a leak code in the main room. If people want to stay and do a leak code, I'm going to do a leak code 101, which is, what am I doing? I can't remember what 101 is. Oh, it's the same tree. So we're determining whether two trees are identical. So it'll be up to you guys after your break, whether you want to go to your breakout room or you want to stay and do a leak code on a breadth first search. Okay, so take a 10-minute break and then we'll come back at 7:30, and then I will have breakout rooms ready if you want to do a breakout room, or you guys can stay with me in the main room.
Asha, hey, real quick, is that print tree function. That's essentially the stack procedure.
What are you looking at?
The right where you just had the
Oh, yeah. Lines 15, yeah,
okay.
yep. You know,
All right, so I'm gonna write that.
I'm gonna put it in Slack in a minute.
Okay, thank you.
Yeah, so the one that we're gonna do, obviously the LEET code, it's like 15 lines of code because I'm doing a whole Boolean test on like what we're doing, like are the nodes the same, right? So
Yeah.
the print line is just a filler, right? For you're gonna put whatever test you're putting in, you're completing in that space, right? But the rest of it is your DFS.
Okay.
Yep.
Thank you.
You're welcome.
I'll be back in 10.
Yeah, at
7:30.
7:30. Yep.
Fantastic.
So wouldn't you, after you have it print out, couldn't you also do a boy, I just had it. So like you have your printed list and then you can have a thing run through the list to find the matches.
Is that what you're asking me? Whether for 101, whether we're gonna do if you find the node? Is that what you're asking me, or are you asking me something different?
No, no, no. So like the one that you're going to do, because you said you gotta check to see if the trees are similar, and then
Yeah.
wouldn't you like compare each list, like have it run through each list to see if they match the numbers?
Yeah, so we're gonna run through each node on each tree and see if they match.
Okay.
Yeah.